Welcome everybody, my name is Oliver Marquardt from Wirebased Institute for Applied Analysis and Stochastics in Berlin, and I will present our work on the role of random alloy fluctuations on the electronic properties of axial indium gallium nitride nanowire heterostructures. This work has been done together with Thomas Koch-Brücki from my institute, Michael O'Donovan and Stefan Schulz from Tyndall National Institute in Cork, Ireland, and Oliver Brandt, Paul Rude Institute for Solid State Electronics, Berlin. The main motivation of using the ternary alloy indium gallium nitride for optical devices is that in principle its bandgap is capable of spanning the whole visible range. On the other hand, it is clear that the ternary alloy is always subject to some sort of alloy fluctuations, and that these alloy fluctuations will have a quite decisive influence on the optical properties of the system. When we want to simulate alloy fluctuations in a system, it appears quite reasonable to assume that as this is an atomistic effect, we will require some sort of an atomistic model, such like empirical tight binding or the empirical pseudopotential method. On the other hand, it is very clear that the computational effort of such a simulation increases with the number of atoms involved, and that means once we approach the larger dimensions of realistic heterostructures, this will result in a very, very large computational effort as well. Even more as we are talking about a random process, and at some stage this will mean we will need some statistical analysis, so we would have to do the simulation for systems that are already quite expensive again and again to achieve some meaningful statistics. A computationally cheap alternative to this would be to use continuum models like the effective mass model or the more generalized multiband K.P approach. Here it is of course clear that these models lack the atomistic resolution that basically are the very nature of these alloy fluctuations. So our question here was, can we maybe find some compromise that allows us to use a continuum framework, so basically to benefit from the rather limited computational efforts of the continuum model while still maintaining a sufficient accuracy to describe realistic heterostructures. Let me briefly illustrate different systems of interest and the corresponding computational efforts with them. If we start with the planar system and pick a small section of such a system, for instance, we have some indium gallium nitride layer in gallium nitride of dimensions of 10 by 10 by 10 nanometers in the simulation cell. That means that we are talking about 87,000 atoms, which is something realistic for atomistic approaches like tight binding or empirical pseudopotential. And also it's possible to do some statistical analysis of such a system. It can be parallelized in a very trivial manner. You simply run the same simulation on different CPUs with each indium gallium nitride layer being set up differently. The atomistic resolution in these models is of course intrinsic, and here for such a case there's basically no demand to use a continuum model. On the other hand, it is clear that these simulations become numerically more expensive once we are looking at larger sections of such a planar system. If we talk about indium gallium nitride nanowires, and we pick a length of around 20 nanometers here around this active layer of the model, assuming a diameter of around 80 nanometers of such a structure, we would expect to have around 1.2 million atoms in the cell, which is still reasonable and can be done with atomistic approaches, but it's quite expensive, and of course doing statistics here becomes very, very expensive then. If we now would go ahead and say, okay, let's take a continuum approach but assume a single atomistic resolution, of course we would end up with similar computational costs. That basically there is not too much of a difference between having a different number of atoms and the pretty much same number of grid points in the continuum model. So we have, in some sense, we have to interpolate the composition of the system in the continuum model. And the question is, how can we map atomistic alloy fluctuations on a more coarse-grained grid that would be useful here for reasonable computational effort within a continuum model? So the general idea that we have is that we basically consider local alloy contents within finite volume elements, pretty much similar as it's also done in some sense within localization landscape theory. The local alloy content can then be either generated or collected from an atomistic picture if we have an atomistic picture available, and we can apply some coarse graining. So basically we simply increase the size of the volume elements to reduce the computational effort, but at that stage of course we lose the accuracy of the atomistic picture, and basically our average alloy contents get basically less and less detail from the actual atomistic simulations. And then once we have this coarse-grained mesh at some point, we can compute the electronic properties within continuum approaches, and in our particular case we have used an 8-band K.P model. While in a first evaluation we will of course take the local alloy contents from some atomistic picture that we compare with, it is clear that also this local alloy content can be produced randomly already within the continuum approach. So our questions are now, how good is actually the comparison to an atomistic picture for those cells where we can still do both simulations, the atomistic one, which here is a tight binding model, and the 8-band K.P simulation, and in this context what resolution or volume element size would be acceptable for a good compromise between accuracy and computational effort. And in the end, is this suited to describe realistic and relevant heterostructures? So, what we will use here in the continuum model is an 8-band K.P Hamiltonian, basically consisting of the bottom conduction band here in black and the top 3 valence bands. That's pretty much the backbone of device simulations to date. In heterostructures, it can be combined with envelope function approach, which basically puts a spatial dependency on effective masses, potentials, so basically band offsets, couplings, and so on, and we replace the case here by the partial derivatives. There's also other contributions that I'm not talking about here too much in detail. So strain enters the simulations via continuum elasticity theory, and also piezoelectric potentials and external potentials and charges can be added. And we will also discuss excitonic effects that are computed using a self-consistent Hartree approach here. The formalism we use is implemented within the Swing software library. It's a generalized multi-band K.P model, and generalized means it's generalized within with respect to the materials that can be used, the shapes of the heterostructures, and the corresponding dimensions, and in particular the level of sophistication, so basically the number of bands involved. However, we will here stick again to an 8-band K.P model. The formalism is implemented within a plane wave framework, and by now our package is installable via a simple package manager systems under most common Linux distributions. As a first test, we compare between an atomistic tight binding model and an 8-band K.P model the simulations of a 3 nanometers thick indium gallium nitride layer with indium contents of 515 or 25% in gallium nitride. Our simulation cell has a size of 10.2 times 8.8 times 7.8 cubic nanometers, and we take this atomistic simulation cell and then translate it into a continuum picture. We start with an initial discretization of 80 by 80 by 80 grid points in the continuum picture, and then apply some coarse graining to 40 by 40 by 40, 20 by 20 by 20, and 10 by 10 by 10 grid points in each direction to see how this more coarse-grained averaging of the local indium contents influences the electronic properties. What we compute then are 15 electron and hole states closest to the band gap. So here on the left side you see the electron states. The black ones are the ones computed with tight binding, and the red one's the one computed with K.P, and here on the right side you see the whole state energies. And Then we apply this coarse graining, so we compute the energies once from the tight binding, then from the K dot P, and then we reduce the accuracy of the discretization of the cell according to this coarse graining levels here. So what we see is, first of all, the spectral range seems to be more or less okay. So the energy difference between the first and the last state are pretty much similar for the K dot P and the tight binding, and the same applies to the holes. What we see if we look at the absolute values, we see that there's a shift here that gets larger and larger with higher indium contents, but as you can see, these shifts go in the same direction within the electron and the hole simulations, and they are of about the same size. So for the transition energies, these shifts are basically non-existent, and we see that still the spectral width of these 15 electron and hole states appears quite okay until a coarse graining level of, let's say, 2, which would correspond to about half a nanometer step discretization. So basically we can say that we have a quite good agreement, a surprisingly good agreement when computing the ground state transition energy, but also the spectral width between the tight binding and the K dot P model up to a coarse graining level of 2 here. Now let's move on to the system that we are actually interested in, namely an axial indium gallium nitride nanowire heterostructure. We assume we have a hexagonal gallium nitride nanowire of pretty thin diameters of 10, 20 or 30 nanometers, containing one indium gallium nitride insertion of an indium content of 5, 15 or 25%, and a thickness of this insertion of about 1, 2 or 3 nanometers. We make use of an orthorhombic cell here to maintain the correct symmetries of the hexagonal wire, and given that we are in a plane wave framework, we of course have periodic boundary conditions intrinsic. We then compute the electron and hole ground state and the excitonic effects via a self-consistent Hartree approach here from our 8-band K dot P model, and per configuration with respect to wire diameter, indium content and insertion thickness, we have computed 500 randomized nanowires for a statistical analysis. The relevant simulation output is then the single particle energies of electron and hole ground state, the charge densities and the charge carrier geometrical overlap, which gives us some idea about the recombination properties. And also we will have a more detailed look at the exciton binding energies. To understand the impact of random alloy fluctuations on an ensemble of nanowires, we perform a statistical analysis of the transition energies as well as on the role of excitonic effects. Now let's first have a look at the transition energies. What you see here are the electron and hole ground state transition energies, including excitonic effects, as a function of the insertion indium content for different nanowire diameters and different insertion thicknesses. And what you see is that the average ground state transition energy of our 500 simulations we have done for each of these configuration points acts pretty much like one would expect it from a system assuming a homogeneous distributed alloy in the insertion. We see that with larger indium content the transition energy goes down, and the same applies to larger wire diameters and larger thickness of the insertion due to the increasing effect of polarization potentials in such systems, which then reduce the transition energy. If we have a look at the variations of the ground state transition energy in all these systems, they account to a few tenths of MeV, which basically means that solely due to random alloy fluctuations in otherwise identical systems, we will see variations of the transition energy of a few tenths of MeV, so basically something like a spectral width already. We find that these variations are largest for large indium contents, thin insertions and thin nanowires here. What we have a look at next is the exciton binding energies, and we see that generally speaking the average exciton binding energies are also largest for thin insertions and thin wires, and they increase slightly with for some systems with the indium content, but in other thicker systems or other wires, we basically see that they start to decrease again then later on. So what we see here is basically the geometrical overlap between the electron and the whole ground state, which gives us an idea about the optical recombination. And we have shown this here with respect to the reference overlap, which corresponds to the overlap of electrons and holes in a system where we have assumed a perfectly homogeneously distributed alloy in the indium gallium nitride insertion. What we see is that in most cases the overlap is larger than in the reference system where we assumed a homogeneous alloy, and what we also see is that in thin wires, which is here on the left side, these 10 nanometers thin wires, the overlaps are still quite close to the values of a homogeneous alloy reference structure. If we go for thicker wires, we see first of all that the electron-hole overlap is significantly larger than in the reference system, but what we also see is that there are quite large variations of this geometrical overlap in thicker wires, and it seems that this means we find a significant impact of random alloy fluctuations on the recombination properties in each individual wire, in particular once we go to wires of 20 and 30 nanometers diameter. Now in the next step, let's have a look at some selected individual systems. So we have here picked some typical reference systems from our whole study. So basically system A is a thin wire, insertion thickness is 2 nanometers, and it's got an indium content of 25% in the active layer. System B is a thicker wire with a thicker insertion of 3 nanometers and 15% indium content. And system C has a wire diameter of 30 nanometers, insertion thickness again of 2 nanometers, and a very, very low indium content. What you see here is basically the electron, which is red, and blue hole state, ground state, charge density, and the exciton binding energy between these two particles for a reference system where we have assumed a homogeneous alloy distribution. And then from our statistics, the system with the maximum exciton binding energy and the minimum exciton binding energy. And down here we see a corresponding histogram of exciton binding energies for 500 simulations for each of these three model systems. So what we see is that indium clusters with individual wires can induce very, very strong confinement and large exciton binding energies. So for instance, here we see that in this system we see a very, very well confined electron and hole, which is certainly due to the fact that we have a indium clustering of some sort here. This is mostly the exciton binding energy of all these systems will be larger than in the reference system, but it can also be smaller, namely in cases like this one, where due to the nature of the alloy fluctuations, due to the fact that they are spread out quite broad, the electron and the hole are rather delocalized, and we don't see such a strong excitonic effect. And you see here that this can differ quite dramatically in terms of the amount of what our exciton binding energy gives us. So such clusters have a large influence in thick wires, but not too much here in these thin wires. You see there is not too much variation of the exciton binding energies here for the thin wire. Reason for this is certainly that there is a strong quantization influence of the semiconductor vacuum interface, which can be more and more neglected once you go to thicker wires. So it's understandable that these clusters have a larger influence in the thicker wires. So we can conclude from this that the influence of alloy fluctuations can be reduced in such systems if you go to thinner wires due to the side facets that then dominate the electron and hole confinement. And once you go to thicker and thicker wires, these fluctuations will take over and govern your localization and your electronic and also excitonic properties. So that brings me to the end of my presentation. Let me conclude. I have been talking about the role of random alloy fluctuations in axial indium gallium nitride nanowire heterostructures. We have seen that generally random alloy fluctuations can be described on a continuum level, and there has been a quite good agreement with atomistic tight binding simulations for our planar indium gallium nitride benchmark system. In the ensemble simulation of axial nanowire heterostructures, we identify a strong influence of alloy fluctuations on the electronic properties, and we see that there is an impact on the single particle energies, but in particular on the binding energy and the charge carrier overlap, and that can be reduced significantly if we reduce the diameter of our nanowire. So with this, I would like to thank you for your attention, and I'm open to your questions written in the chat. Thanks.